Good morning, everyone. So how are you guys? Yeah, I know. So, remember what we have been doing. So basically, you'll see that I'm going to write this utility maximization problem and the objects that we have found and that we learned. Remember, we learned about the demands, we learned about the indirect utility function, right? And then you're going to see that today we're going to see a very similar problem, and then we're going to fill out this table for that problem as well. Okay, so you'll see I talked a little bit mysteriously, right? But we'll see how things work, right? So remember, we had the utility maximization problem, okay? And then remember we said consumer's aim, consumer's objective is actually to maximize utility. So suppose we have the n good case, right? And of course we're maximizing with respect to these x1 up to xn variables, right? And then we said subject to the budget constraint, p1 x1, p2 x2, pn xn, which should be equal to income, right? So we talked about these budget constraints and all these stuff. So this was our problem. So don't forget that we call this, okay, we call this guy the objective function. Okay, so this is your objective. And then we basically call this the constraint, okay? Now we'll see why. You see that these will be important when we actually consider a similar problem, okay? So this is basically our objective function, and this is our constraint, right? So when we solve the problem, we got the demands, right? So let's call them demands. And then you'll see that these demands, we'll come to this later, but these demands are called Marshallian demands, okay? So we'll see, so they are actually called Marshallian demands, okay? You'll see why we need to make this kind of a distinction, okay? But these Marshallian demands were demands, right? So basically they were, we said that, oh, this is x1 star, which is a function of what? Remember, I told you, I'll keep asking you this because it will be very important. Prices and income, right? So this is basically P1, P2, Pn, I, right? And then we had Xn star, so Xn star, P1, P2, Pn, and I, right? So these were the demands. So then we said that, well, these are the maximizers, right? So when we actually put these guys back into our objective function, which is the utility function, when we plug them back in, what was the function that we were getting? It's called indirect utility, right? So basically, and here let's call this indirect utility function. So, and remember that this is called a value function. So this is actually a value function. Okay? So the indirect utility function was something like this. It was a function of what? It was a function when you plug these guys back into this utility. So it was a function, you tell me, u, x1 star, x2 star, xn star, but basically all these guys are functions of these guys. So this indirect utility function is a function of, again, prices and income, right? So this is going to be P1, P2, Pn, and I, right? So this was the indirect utility function. So keep this table in your mind because we're going to fill out another table right here, okay? You'll see. Now let me ask you this question. Suppose the income, the maximal utility, right, that you get from here is, let's call this U bar, okay? Suppose the maximal amount of utility you would get from this utility maximization problem, you found, suppose it's U bar. So let me ask you this question, okay? So let's go back to our basics, right? So how we figured out this problem. So let me ask you this. So let's say I put here y, I put here x, and suppose this is that utility level, okay, U bar. Now, suppose I fix this utility level, and then I say that, okay, let me look for the minimal amount of expenditures, or minimal amount of budget, you might want to think of it, which is going to give this utility level, okay? So, for instance, my first candidate is a budget line like this. So let's call this E1. Do you think E1 is enough to get utility level U bar? No, right? You don't have enough, right, income, and of course it's not only income. Remember that your budget set is not, the points on you, right, on this indifference curve are not affordable for you, right? They're not in your budget set. Now, okay, so think of this. So suppose, let me call this, I don't know, E3. So do you think E3 is the, let's say, the expenditure level, okay, that you're going to, the money that you would spend on these goods? Do you think E3, can you reach a utility level with a budget, right, with expenditure E3? Yes, right? So you can actually, let's call this, I don't know, point A, right? So basically you can afford to have, if you consume this much X, and if you consume this much Y, you're going to achieve the utility level U bar, and it's affordable for you, right? It's in your budget, basically, it's in your budget set. Now, but is this the minimal amount of expenditure? Can you do better? Right, where is better? If we go again, so maybe I can just go a little bit down. Where would I, if I'm looking for the minimal level of expenditure, where would I stop? Right, again, so some point like here, right? So let's see. Okay, so let's call this E2, right? So let's call this, I don't know, point C or B, okay? So you see that the minimal amount of expenditure is going to be achieved at point C, right? So let's say that, A, at A can get U bar, but can spend less, right? And basically at C, it's actually the minimal expenditure to get utility level U bar, okay? So does that point C look familiar? Right, so it looks like the point where we considered in the utility maximization problem, right? So there, what did we say? We said that, if I had this much, right? If my budget constraint is this, right? If I had E2 level of income, right? And with the same prices here, these are all parallel, so bless you. The price ratio is minus px over py. So you see that, given those prices and income level E2, so we basically, what is the highest level of utility you can achieve? When you were trying to do the utility maximization problem, you told me, hocam, it's U bar, right? Now I ask the same question from the other way around. Suppose I'd like to achieve the utility level U bar, what is the minimal amount of expenditure I should be making, right? And then you tell me, hocam, it's E2, okay? So this is called, so this problem that we have written here is actually the primary problem, okay? So this problem that I mentioned, the reversed version of it, is actually called the dual problem, okay? And you're going to see this later maybe in your other, like math courses and such in linear programming, you're going to see these kind of stuff. So this is the primary problem. And the problem that I mentioned is going to be called expenditure minimization problem, okay? There, you're going to have this utility level, your objective function here as your constraint, because you want to keep that utility level at u bar. And then this is going to be your objective function, okay? So this new problem that we're going to consider is called expenditure minimization problem, okay? So this is actually, so let me write this so that you would have nice notes, okay? So expenditure minimization, okay? So, but you see that problem is very similar. Now, you were looking for the minimal amount of expenditure, right? So basically, minimum, again, x1, x2, xn. So you would like to minimize, right? Your expenditure, which is p1, x1, p2, x2, pn, xn, okay? Subject to, this time you want to reach a certain utility level, right? Subject to what? Utility x1, x2, xn, which is equal to u bar, okay? So you see, this is basically, so you see that this is actually called the dual problem. In the dual problem, the objective and the constraint, it switched places, okay? So this is basically, so let's write this. So this is the dual problem. Okay, it's the dual of this problem. So basically here, as you see, the objective function is now this. Objective function. And the constraint is now this. Okay? So the constraint are, you see they switched places. Now, basically the demands, so you'll see that we're going to solve, so we know how to solve constrained optimization problems, right? We don't care whether it's a minimization or maximization, right? So now the objective function and the constraint, they switch places, fine. So, but we can still use, right, if we have these nice properties that we have. Actually, here we don't have to deal with, remember, in order to solve this, what did we say? We said that this utility function should be, so that those conditions were necessary, both necessary and sufficient. What did we say? Utility function should be? Do you remember?
Concave.
Right? Concave, or at least quasi-concave, of course differentiable and such, but remember we said quasi-concave. Here you see that our objective function is basically linear, right? So it's both concave and convex, so you see that is automatically satisfied. And then remember we said that we use it when we have interior solution, right? The Lagrangian and such that we considered. But basically, we know how to solve this, right? So we know how to, we're going to form our Lagrangian, and the demands that we're going to get from here, you'll see that they are going to be called Hicksian demands because of the people, so Marshall is due to Alfred Marshall, who first basically came up with the demand and supply curve, and who is actually responsible for, so later we'll see, but when you draw the demand curve, basically how do you draw it? So when you draw the demand curve, how do you draw that? So you put x here, right, the quantity of x here, let's put, so you put quantity here, quantity of x here, and here you put what? Prices, right? But remember the demand functions, and you'll see that demand curves that we considered. So basically I can put here x, for instance, and this is price of x, right? But when I write down the demand curve, I write it like this, right? X star, so we basically px, py, and I, right? And when we have the demand curve, we keep this guy and this guy constant, so that we just look at the change between, like how things change when there's a change in price, right? So basically, but how do we usually write down these kind of, how do we usually write down a function? So think of this guy as your y, right? And what changes, we know that px, so this is sort of, think of it as f of x. How do you write this? You put x here, right? And you put y here, right? Usually. But when we write down the demand curve, apparently what do? We put x here, right? And we put y here, right? So we put, right, so this guy here, and we put this guy here. So most of the time, it's actually right like this. So y is now the value of the function. It's not good y, okay? So think of it like this. So basically, and here x, and here you put, for instance, your x star, okay? But you see that this is reversed. It shouldn't be. Usually the tradition is to put the variable which changes here, right? And then the value here. So actually, Alfred Marshall is the one who's responsible for that. The first time he drew those curves, when he drew those curves, he actually put px here and x here, quantity of x there, okay? And then that's how things, that's why we put it like that. But usually, like, if we would like to draw those curves, because those are just functions, we should be putting, let me call this quantity so that you would see it better. We should be putting quantity here and price here, right? So, but that's why it's actually, this is called Marshallian demands, okay? These type of demands are called Marshallian. These type of demands that we're going to get from here, they will be called, you'll see, Hicksian demands, because they're due to, John Hicks, okay? Who, again, the economist who found them, okay? So these are called Hicksian demands, okay? Now, when I get my demands from, suppose I solve this problem. We're going to solve it, don't worry. Suppose I solve this problem, and I get my demands, okay? So usually, later, you'll see that I'm going to put here an H to distinguish between the Marshallian and the Hicksian demands, but we'll see this later, but this is going to be a function of what? Now you guys tell me. So this demand, when I solve this expenditure minimization problem, this demand will be a function of what? Prices and this time utility, right? Remember, because yes. So right, prices and this classroom is, like a laboratory, right? So it's like a lab, so we have weird creatures around. But, right, so it's actually the prices, and as you said, Hocam, it's not income, because here we're kind of looking for the minimal amount of income we need, or minimal amount of expenditure we need, right, given those prices. And we would like to reach a given utility level. So this is going to be a function of the prices and U bar, okay? So this is important. And actually, that would be the difference between the Marshallian and the Hicksian demands, that the Marshallian demands would be a function of the prices and income. Hicksian demands would be a function of prices and utility, okay? So again, we would have another value function here. Basically, when you put these guys back into your objective function, okay, then you're going to get what we call, I'm going to write that down, so just keep that in your mind, but basically it will be called expenditure function, okay? Again, this is going to be a value function, as we said. So the value function of this problem is going to be called expenditure function, and it is basically, so we're going to call this E. So this expenditure function is, you're going to get this when you plug all these guys back into your objective function. So basically P1, X1 star, P2, X2 star, right? Pn, xn star. Therefore, this expenditure function will be a function of what? So it's going to be, if I plug x1, which is a function of all these guys, x2, which is a function of all these guys, xn, which is a function of all these guys, this guy is a function of what? Prices and utility, right? So just keep this in your mind. Okay, so this will be important, okay? So this is basically the expenditure function. So basically it is when you solve this expenditure minimization problem, you get your demands, right? When you plug them back into your objective function, you get the minimal amount of expenditure. The function who would give the minimal amount of expenditure is called expenditure function, okay? Is that clear? Good. So now, let's actually, so because we have figured out how to solve the utility maximization problem and such, we can basically, you know, like solve this problem as well. So let's do this. So basically, so let's actually do that. But before we do this, why do you think people wanted to introduce this expenditure minimization problem? Why do you think they wanted to care about the dual? We know how to solve the utility maximization problem, but why do you think they wanted to introduce this expenditure minimization problem version? Huh? Saying it's similar, right? So it's you'll see that the first order conditions are similar as well. So, but why? Why do you think? Yes. So, but it's a similar problem, but
Maybe that utility is the rank, so we actually should care about how.
Actually, it's yeah. I mean, you guys are almost there. So, do we observe stuff in the you know, like, do we observe utility in real life? No, right? So this is actually that's our objective function, and right. So and basically, we don't observe these utility functions, but do we observe expenditures in real life? We don't observe the utility levels of people, right? But we observe expenditures, right? So we observe expenditures. So basically what you can do is that you can just set some level, you know, like, because you're not solving for it, right? You can just set some level of utility, or you can say that, oh, I want this to be the same for everyone, or I want these guys to keep their whatever utility level they had before, and then I would like to consider this problem. So expenditures are, you know, expenditure data, they are available in real life, so it is actually much easier to link this expenditure minimization to the real life data, okay? Whereas for the utility maximization, because this is the one that you search for and you don't know those maximal utilities, okay? So that's why they wanted to actually introduce, there were also some other reasons you'll see, but they wanted to introduce this problem, okay? Because we do not observe utility functions basically in real life, okay? Now, let me actually make a remark. So let's write this. So let's call this a remark, okay? So basically, remember the indirect utility function was something like this. P1, P2, Pn, I, okay? And then remember we said that if we keep this utility level, let's say suppose this utility level is U bar, and if I want to achieve that utility level U bar with these prices, this is actually called the expenditure function, okay? Now basically, this is going to give me the minimal amount of expenditure you need to make in order to reach this utility level U bar, okay? So if you can basically, so here, the amount of money that you spent is how much? In this utility maximization problem, how much is your expenditure is equal to your income, right? But remember, these expenditure and income, you can use them interchangeably when? When we have More is better, right? So basically, but here, this is actually how much money you spent, right, in order to get U bar. And then basically, in order to get U bar, you need to spend this E amount, right? And when you spend this E amount, the maximal utility you get is U bar. So just notice that these two functions are inverses of each other, right, with respect to the last argument, right? So basically, so you'll see what I mean, inverses of each other, okay, when with respect to last argument, okay? So basically, it means this: if you put this expenditure function here, if you plug this here, it's going to give you utility, okay? And basically, if you put this indirect utility function here, it's going to give you this expenditure, okay? So these guys are inverses with respect to the last argument of each other with respect to the last argument. So just keep this in your mind. Now, let's actually move on. So let's try to solve this problem then. We know how to solve, right, constraint optimization problems. So let's do that. We're going to form the Lagrangian, right? And then basically we're going to solve. So we know it's going to be easy for us now because we know how to deal with those stuff, right? So basically, so let's solve the problem. Basically, let me form the Lagrangian, right? And don't forget that for this constraint, I can always write, so, or I say U bar minus utility x1, x2, xn equals to 0, okay? So you can always write the constraint like this. So let me just form the Lagrangian. So how will I form it? My Lagrangian will be, right? So I write down my objective function, p1, x1, p2, x2, pn, xn, plus lambda. We said now what is my constraint? It's u minus, right? Utility function, u bar minus u of x1, x2, xn, right? So you see, again, it's the same problem. I start taking derivatives with respect to these variables. This time, when I take derivative, it's going to be p1 minus lambda, right? Del u over del x1, which is equal to 0, right? And then we have del L del x2, p2 minus lambda del u del x2, which is equal to 0, right? We know how to deal with these guys. And then I go, and this is going to be my nth condition, xn. So this is pn minus lambda del u over del xn, which is equal to 0, okay? And then we had this condition. So we take the derivative with respect to lambda, which is going to give us the, when I take the derivative, constraint, right? So this is basically, so I have u bar minus u of x1, x2, xn equals to 0, which is nothing but my constraint, right? So basically, again, as we did before, when we look at here, so suppose consider, you know, like from I and double I, right, from the first and second conditions. For instance, I have P1 equals to lambda times del U del X1, P2 equals to lambda times del U over del X2. When I take the ratios of these guys, okay, these lambdas cancel out and I'm left with what? P1 over P2 equals to del U over del X1, del U over del X2, which is nothing but, what was this? The ratio of the marginal utilities is MRS, right? Marginal rate of substitution. So this is, you see, exactly the same first order condition that we have gotten, right, before. So you see it's exactly the same. So the same as before, right? Now, but when you get this, of course, you're going to plug this guy, whatever, and then back into your constraint, right? And then you're going to solve this problem, okay? So this is basically how we are going to solve this. So let's actually go over an example, okay? So this is basic just to show you that these guys, these two problems, you see, would lead to the same condition as we considered, that the ratio of the prices, right, the slope of the budget line should be equivalent to MRS, right? So, or in many ways we mentioned this, right? Now let's solve problems. So we have considered, remember, Cobb-Douglas. Let's try to figure out that the demands that we have gotten in Cobb-Douglas, let's see whether these guys, it's going to give us exactly the same point, right? Remember the graph that we drew? We basically said that it's actually the same point, whether you maximize utility or you minimize expenditure to reach that utility level, you're basically getting exactly the same point. So now let's try to see whether that is the case, okay? So now let's consider our good old Cobb-Douglas case, okay? So let's do this. So basically, here's an example. Okay, so recall our Cobb-Douglas utility maximization problem. Okay, so recall utility maximization with Cobb-Douglas utility. Okay, so basically we had this problem, u of xy, right? So basically you want to maximize this utility. So let's do this. Maximize utility xy, okay? So subject to px, x, py, y equals to I, okay? And remember when we solved this, we got these, and of course because it was Cobb-Douglas, the utility function was x to the power alpha, y to the power beta. And as I said that we solve for the most general case, but for the sake of simplicity, just assume alpha plus beta equals to 1, okay, so that things will be less messy, okay? So basically, so we have this, and remember our x star was what? You don't have to memorize it, you can always solve it, but you know, it was something alpha times I, right, divided by px. Y star was beta times I divided by py, right? So these were our demands, right? So you see that it's a function of px, py, and I, but for the Cobb-Douglas case, because it's special, it's not a function of py, right? And this is y star, right? So these guys were the demands. So these are actually called, as we said, the Marshallian demands, okay? And then we actually had the indirect utility function, right? So the indirect utility function, basically if we write this down, which is a function of px, py, and I. So basically when you put u, x star, y star, so when you put x star, y star there, we would get alpha I px, right, to the power alpha, beta I py to the power beta, okay? So this is basically, and we said that this is alpha to the power alpha, beta to the power beta, right? And then I to the power alpha, I to the power beta, so alpha plus beta adds up to 1, so this is I, divided by px to the power alpha, py to the power beta, okay? So this was my indirect utility function, okay? So this is actually what we had. Now let's solve the expenditure minimization problem, and let's see whether we could get exactly the same point, right? Because this was my argument. So I said that, oh, okay, so suppose you had this budget line, and this is the maximal utility you can reach, U bar, right? So let's call this is your expenditure level, whatever, or this is your income, right? And then this is, and when you ask the problem from a similar point, right, you say that, oh, you want to fix this utility level, you're looking for the minimal amount of expenditure to reach that utility level. We said it's actually your income, right, to begin with. So basically, the demands when we solve both of these problems, they should give me exactly the same point, okay? And let's see whether basically that is the case or not. It's actually, right? So let's try to see whether we would get exactly the same point, okay? So let's do this. Now we're going to write down minimize, right, px times x, py times y, xy, right? So it's going to be similar. Subject to, this time, what is my constraint? You guys tell me. Now I'm going to reverse these guys, right? I'm solving the expenditure minimization problem. My constraint, right, as you said, that hocam u of xy equals to u bar, or u bar minus u of xy equals to 0, okay? So this is basically the case. Now let me write down the Lagrangian, okay? So let's actually try to figure this out. So let me form the Lagrangian. My Lagrangian is px times x, py times y, plus lambda, right, u bar minus u of x bar, right, u of xy. And now del L, so let me write down the conditions. First, I take the derivative, right, partial derivative with respect to x. So this is px minus lambda times del u over, and of course I know this, let me write this. What is it? So this is, my utility function is x to the power alpha, y to the power beta, u bar. So you just write this, right? We solved it for the general case. So basically, then what is the derivative with respect to x? Partial derivative with respect to x, it is alpha times x to the power alpha minus 1, y to the power beta, right? Which is equal to 0. And then my second condition, del L over del y, py minus lambda. Now my derivative with respect to y, it's beta, right? Y to the power beta minus 1, x to the power alpha, okay? So this is a very common mistake, that when you take these derivatives, you always forget. When you take the derivative with respect to y, you forget x. When you take the derivative with respect to x, you forget y. So that's a very typical mistake, okay? So make sure you take the derivatives properly, okay? And then, so here, you know, you usually forget these guys, okay? Or this guy. And then the last one is the partial derivative with respect to lambda. And then this is nothing but your constraint, right? Y to the power beta, which should be equal to 0, okay? Now, from here, again, we do our usual stuff, okay? So from here, I get what? Px equals to lambda times alpha x to the power alpha minus 1, y to the power beta. Py equals to lambda beta x to the power alpha y to the power beta minus 1, right? So from here, and I just take the ratio of these guys. You can always think of it that you're actually equating lambdas, okay, in this case. So basically, from here, what do you get is, remember, so I am going to be left with what? So there's alpha minus 1 here, so this goes away. I'm left with x here, right? There's beta minus 1, this goes away. I'm left with y here. So it's basically px over py, alpha over beta, right? Y over x. So if I get y from here, let me put all these guys. Beta over alpha, right? Px over py times x. Does this look familiar to you? Actually, we know, right? This is exactly how did we call this when we get this relation from the utility maximization problem? We call this income expansion path, right? Or income consumption curve, right? So you see, you get exactly your income consumption curve here. So this is the same. We know that it's going to be the same, right? So you see that it's the same. And then now to find the demand, remember we were putting this back into the constraint, right? So let's do that. So let's actually put that guy into our constraint, so which is basically x to the power alpha. So instead of y, I'm going to write this, y to the power beta. So basically beta over alpha px over py, right, times x to the power beta, which is equal to u bar. Okay, so I plug this into my budget constraint. I plug this into my constraint. This time the utility sort of constraint, right? So then from here, what do I have? I will get my x star from here. So let's actually get this. So basically here it's x to the power alpha. This is x to the power beta. Beta alpha to the power beta px over py to the power beta equals to u bar. Okay. So I know that this is x alpha plus x to the power alpha plus beta is 1, okay? So basically, so this is 1. So I get x star, my x star will be a function of, I need to put all these guys into that place, to the power beta py over px to the power beta times u bar, okay? So you see that this is my x star, okay? So, and then let me find my y star. So you see that for me, the easier way is that plug this back into the relationship between x and y, right? We know that this is giving us the relationship all these optimal x's and y's should satisfy. So basically just plug this back into there. So what is y? So from here, y star is going to be, when I put this beta over alpha, right, px over py, and then this is going to be, for x I put this, beta py over px to the power beta times u bar, okay? And then from here I get, so if I flip this, it's going to have minus 1, so this is going to be alpha over beta to the power beta minus 1, py over px to the power beta minus 1, u bar. Okay, so I have found my demands. Remember, we have said before, don't worry, I'll put this back up, but just a second. Remember here I said that these demands should be a function of the prices and u bar, right? And this is exactly what we have. This is a function of the prices and u bar, right? And this is a function of the prices and u bar. But how can I convince you or your grandma, let's say your grandma learned a little bit of, you know, like math by now because we kept asking her so many questions, right? Now suppose we would like to know, but she's asking you, but you told me that it's going to be the same point, right? But how will I, but this x star that you have found here was this, and the x star that you have found here is this. So how can you show me, you know, like that these are exactly the same points?
Equal them?
Huh?
Equal them with each other.
But they should be equal, so it should be somehow. But the issue is that, the problem is that this there is no u bar here, okay? So if I had all numbers for these guys, I would get exactly the same number, okay? But now here, I didn't give you numbers for px, py, income, or u bar, whatever. So then that's why you have all these, you know, like sort of px's, u bars, floating around, okay? But basically here, you don't have u bar, okay? But we know that this guy is u bar, right? So let's plug this. So and let's see whether we can show your grandma. I know that this is u bar, okay? So let's say that for that u bar, let me plug that okay? So which is alpha to the power alpha, beta to the power beta, right? Times I divided by px to the power alpha, py to the power beta, okay? So let's see if, this is our only chance. Hopefully we'll get exactly the same demand, okay? So let's see whether that is the case. So let me put, so this is x star. I'm going to put alpha, beta, right, to the power beta. So then I'm going to have basically py, px to the power beta. Instead of u bar, I write this. Alpha to the power alpha, beta to the power beta, times I divided by px to the power alpha, py to the power beta, okay? So let me write these guys like this. Px to the power beta, alpha to the power beta, beta to the power beta, okay? I didn't do anything, I just, so that you can see all the cancellations, okay? So you see that these guys cancel out. This goes away, right? This goes away, this goes away. So I'm left with alpha to the power beta, alpha to the power alpha times I divided by px to the power beta, px to the power alpha. So I can write this alpha to the power alpha plus beta times I, px to the power alpha plus beta, right? And we said that these guys are what? 1. So basically you see that from here I found x star alpha times I divided by px. Does it look familiar? Right? So we actually, we made our point, right? So you see it's exactly the same demand as before, okay? So you see, if I had given you the numbers, you would find exactly the same x star, right? If it's like 5, you solve the expenditure minimization problem, you solve the utility maximization problem, you're going to get 5, okay? But because we're considering the most general case, that's why we had initially these guys, okay? So is it clear? So we actually, it's a little bit tedious, but we showed that it's actually the case. Now, the expenditure function, okay? So let's give a break, right? So, and then we will continue.